to everyone at home. This is just, we're going over the warm-up, which you guys don't have a new warm-up paper, but you can just do this for extra practice here. So we're finding all kinds of stuff about this problem here. So Delta Math will randomly call students for me. So let's see who gets to tell me the domain. Maddox. Okay. -2 to positive infinity. Do you guys agree? I think that looks good. There. I think that looks good. -2 right here, you're not going to go further than that. You know for sure that's the case because you could take what's inside of the parentheses, the x plus 2, and it has to be greater than 0. So that's x is greater than -2. So that is our domain. Let's see. Probably not here. Reese, what is our range for that one? Very good. And that's always our range for a log. Then we need x intercepts and y intercepts. So let's see. Jackson, what did you get for those? Is it? Okay. On mine here, let's see, if you got 5 log x plus 2 minus 1, make sure your equation's right. Okay. Okay, good. That is our y-intercept. So 0, 0.505. And then the x-intercept, what are we going to get there? Good. So that will be our x-intercepts and our y-intercepts. Let's see, next we need vertical asymptote and horizontal asymptote. So let's see who it's going to pick here. Grace has already been called on. No, it's not here. Ron's not here. Grace. What would we have? First of all, do we have a horizontal asymptote or a vertical asymptote for this one? Okay, good. And so we do not have a horizontal, but we do have a vertical. What would our vertical asymptote be? Good. And what equals -2? Is it x or y? X equals -2 because x equals is going to be our vertical line. All right, next we need positive and negative. All right, let's see who it's going to get here. All right, Braden. Where is this graph positive? Very good. Because positive means we're looking at it's above the x-axis. That starts right here at that x-intercept. And then over in this direction forever it is positive. So it's a positive infinity. Very good. And Braden, what'd you get for negative? Very good. I like that you stopped at -2. Part of me wants to put negative infinity because that's that direction, but this graph actually doesn't exist over there, so you have to stop at -2 right here. So from -2 to -0.415. Okay, and like to think about that, if you put x equals -2 and x equals -0.415, that'll kind of like section off that part that's below the x-axis. So that sort of lets you see, oh yes, everything falls within that little area right there. All right, questions so far? All right, let's see next. We need increasing, decreasing. All right, Connor.
Increasing is -2, positive infinity.
Very good. Decreasing? No. Okay. So, and notice here that that is the same as our domain. It's always increasing, but when we say it's always increasing, we don't put negative infinity to positive infinity automatically. We have to look at what the domain of the function was. And so that goes here. And then we've got concavity, so we're concave, concave up and concave down. We've got, oh, it's not here, it's not here, no, it's not here. Caitlin. Very good. And we're never concave up on this one. Again, it's that same thing. That is your domain. So for increasing, decreasing, or concavity, it should be your domain. You just got to decide whether it's concave up or down, or increasing or decreasing. There. And then the last thing is that in behavior, as x approaches blank, f of x approaches another blank, and then for the other side, as x approaches blank, f of x approaches our other blank. So, let's see who gets this one. Blaine, this one's yours. So, what would we put for that first one? So that being our left side of the graph. Yep, as x approaches -2, what does our f of x or our y values approach? It's negative infinity because this is the time we're looking at our y values and it's going down. So basically you got three options of what can happen here. It can either go down forever, which is going to be negative infinity. It can go up forever, which is going to be positive infinity, or it could level out at a number. So you might get like 7 or 2. It doesn't happen for this one, but it might happen. There. All right, so Blaine, for the other side, what should we have? As x approaches no. So what we want to think about for this is we're thinking about, so that is our x-intercept, like where we cross that x-axis, but within behavior, we're thinking about the very ends of the graph over here. So on the left-hand side, it was -2, because that's as far as we can go to the left, right? On our domain, that's our left-hand point. On the right-hand side, we can go past this point right here. We could keep on going in this direction forever, right? So our right-hand point of our domain, this infinity, that's going to go here. And basically, this number of your domain always goes right here, and this number of your domain always goes right here. And so when we look at that side, on this right side of the graph, what's happening to the graph? Is it going up forever, down forever, or leveling out at a number? It's going up. It looks, especially if you zoom out, it starts to look like there's a horizontal asymptote there. But if you think back to what we had before, there's no horizontal asymptote for this one. So it just goes up forever. It's not very steep, but it does go up forever. So you would just have positive infinity there. Okay, questions? All right, so that just gives us a little bit of review on that. Let's look at last night's homework. Answer key was wrong on that first one because surely I caught that last time and just didn't change it. I need to quit doing this where I scan my answer keys in because then it makes it really hard to change it. I got to go back and scan it again and upload it and do all that. Whereas if I save it on the computer, I can just, if I write it in on the computer, I can do that. But you guys will find a lot of my stuff is very old, and I don't like redoing all of it because I don't have time for it. So right here, what you should do on that one is you should adjust your interest rate. So you'll do 0.08 divided by 12. So you should have 0.006 repeating for your rate. If you'll add 1 to it, you're using this number right here instead of that 1.08. And 5 years should be months instead, so I should put 60. So it's going to look like this, 5,000 times that number to the 60th power is what I should have done here. And that gives you 7,449.23, which is the correct answer for that. That was a terrible error on the very first, more easy problem. I'm not sure what else was on that. Okay. Other questions for the worksheet? Other things you're not sure about? Okay, I'm pretty good about it. Okay, if you do have something and you don't want to ask right now, we'll have some time to work, I think, at the end of class today. I don't think notes will take till the end, so ask me then if that's the case. So we're going to do another set of notes today, which finishes up this. This section is too long to do in one day and not quite long enough for 2 full days, really. But if we get ahead, we will. More of what we were doing yesterday. It's we'll have a few different types of problems we didn't see yesterday. So I'm still recording on. Alright, so initially 750 virus particles infect a person. The virus replicates at a rate of 157% per hour. How long will it take for the virus population to grow to 5 million? In this particular case, we have a growth problem. Sometimes it is difficult to know whether or not you should use continuous growth or whether or not you should just use our A times B to the X formula. In general, really you could probably do this problem with either one and it would give you different answers, but they would be relatively close. And you could probably, if you were in like a research setting, you would, look at how your data is behaving, and you would compare it to what you're seeing in experiments and decide which one is most accurate. For us, since we're not in a research setting, if I want you to use the continuous function PE to the RT, I will put continuous somewhere in the question. So I will say that I would say the virus replicates continuously at a rate of 157 or something like that to indicate to you that I want you to use that formula here. So since that's not here, we're just going to use A times B to the X for this question. So we have 750 particles. What number are we going to use here for our B value? It is 2.57. It seems like it should be 1.57. But you have to do, you're always doing 100% plus your growth rate. It's just your growth rate is so high here that it already looks like the 1 has been added to it, but you get 257, which is 2.57. And that would be raised to the X power. We don't know what X is. We need to know when there are 5 million virus particles. So we're going to put 5 million over here. I only recently found this out, and I felt like as a math teacher it was a shame that I did not know this. Did you guys know that in lots of countries they use a comma as a decimal point? And a decimal point like we use a comma. That is maddening to me. That the world couldn't get together on that. And that I somehow was a math teacher and I did not learn that till last year. So, anyway. And it is disturbing to see somebody write 2.57. That just aggravates me to see it like that. It's so ingrained in my mind that I just can't possibly like it the other way at all. I had not ever seen it before because I think any students I have had from outside of the United States, for the most part, have came from Spanish-speaking countries in either Mexico, Central America, South America. I have not really had any students from the only other student I can think of. I did have a South Korean exchange student one time who was so great, but he did not do that. But they may have just taught him not to do that. I'm not sure what Korea does, but so all of those countries pretty much go with what we use. But I was watching Spanish videos, trying to find some for my students who I had last year that did not speak English very well, from a lady in Spain, and that's when I discovered it. And in Spain, apparently, they do it that way. A lot of Europe does it that way, which is crazy. So, anyway. Side note there. Here, we're going to divide by 750. We've got to get rid of that 750. So, 5 million divided by 750 is going to give us 6,666.6. Repeating, 2.57 to the X power. And then, Reese, what do I do to get rid of that 2.57? I can't divide it. Because it is not 2.57 times X. It's 2.57 to the X power. Not a root. It's log. We need to do log with the base 2.57. Which is the main reason that this ends up in this section anyway. Because those are inverses of each other. So, to type that in, we would have log of that answer that we just had divided by log of 2.57. We're at 66% today. Oh, you're back. You're back up. So maybe we're starting to get on the other side of the spike. I'm not sure about that though. All right, so we get 9.328 is our x. What's that measured in? It is hours, because this was our rate was per hour here. So 9.328 hours. Now I just made up this question, but I think things like this actually happen inside of your body whenever you're exposed. It's crazy. Now, my exact rates and exact time periods. I'm sure everything's different from different virus to different virus. For me, the whole, and I have to imagine, like, obviously coronavirus is a horrible thing, but, like, from a research standpoint, it is terribly interesting to, like, learn more and more about how it affects things and what's happening and trends, and then, like, we start to think we know something, and it seems like that changes. So it's kind of interesting stuff. I'm sure that if you were working in a lab where you were monitoring this and doing experiments with different things, you would really be looking at a lot of this stuff here. All right, so this is a couple years old, but this, I think, when I looked these up, this was the population of India, so this is relatively close to accurate. So if the population of India is currently 1.353 billion, it is growing continuously at a rate of 1% per year. What will the population of India be in 20 years? So here we've got continuous for this. Maddox, how would we set up this equation? Very good. And so you got two options on how you deal with that billion. You can either do like I have done here and plug it in as just the 1.353. And what I'm going to do when I get my answer, I know that it is in billions of people, not just people. All right. Or you can put that in, put all of the zeros, and then it's going to give you the actual number there. You won't have to have it in billions. So it's up to you on how you want to do that. You got less room for error with those zeros if you do it this way, which is why I chose to do it this way. So we got 1.380 billion, which seems like misleadingly not a very big difference. Oh, of course it seems like not a very big difference because that was only 2 years. Let's go back up here and add that 0. Okay. I will still say though, this deceivingly seems like it is not. So I should run to 3. I do 3 places. Not a huge difference going from 1.3 to 1.6, except for you got to remember this is in billions of people. So we're talking like 300 million people over 20 years, which is the size of the United States, roughly. Roughly the population of the United States being added in 20 years. So, although I will say that I think even in countries where birth rates were skyrocketing and like population was growing out of control, I think we're seeing those drop from where they were. So this trend may not continue for the next 20 years there. And like China has actually sort of reversed trend and is now like they've changed. They had the one-child law where you could only have one child. Well, if you didn't, you had to pay a lot of taxes. Is how it kind of worked out. But they changed theirs a while back to two children, and now they've changed it again to 3 children because they're seeing in their population they have a lot of old people and not very many young people working to take care of the old people. So they are kind of upside down on their population. It's kind of a issue there. So, but what they found is when they raised it to 2 and then to 3, it didn't do much for their birth rates. Because people have kind of accepted that as a way of life, and they're like, oh, 3 kids, I don't want 3 kids. So it's interesting there, that policy and how it's affected things. So in 2000, population of wolves in a certain area was 457. Number of wolves increases exponentially at a rate of 3% per year. Predict the wolf population in this area in 25 years. So, or in the year 2025. So, let's see, Blaine, how would we set this one up? We will, it's 0.03, and we need a 1 in front of it. So the X there would represent our number of years. Do we know how many years it is going to be? It'll be 25. So we could go ahead and plug that in here. There. So the exponent in these equations is your time. So in this case, we're going from 2000 to 2025. So we know our amount of time. Sometimes we don't know that, so the X has to go there. But in this case, we do. So 457 times 1.03 to the 25th power. It's going to be 956.856. But here is an instance where it doesn't really make sense to round to 3 decimal places when we're talking about wolves. Population, it doesn't really either because you can't have a piece of a wolf. So a lot of times you'll see these ask you to round the nearest whole wolf. Okay, questions? All right. Try this next one on your own. Okay, so for this one, you've got your equation that's given to you, so you're using that. It's want to know how long it will take for it to drop below 60 million. So we're setting this equal to 60 million. To solve that, you need to divide here by that 60,360,000. That's going to give you e to the negative 0.002t equals this number. You'll need to do natural log of both sides to get rid of that e. And then that just leaves you with negative 0.002t equals this decimal here. And then you finally just have to divide on the last step. So I got 2.991, which is about 3 years, which would be 2021. I wonder if their population has dropped below 60. I think I used actual numbers there, although I'm not sure there are like accurate census numbers in that short of period of time to check. So, lots of Europe is seeing like population declines like that right now, and coronavirus is not helping that. Especially Italy was hit really hard early on. They have an aging population. So interesting things to look at. Have you guys ever seen the video? Has any teacher ever shown you the video with the dots that show up for each million people? And it goes from like way long ago up until current day. Might have to find it. Some of you have seen it. It sounds like I may have shown it to you guys in Math 1, possibly, because I usually show it to them when we do exponentials. I might show you guys that while we're doing our work, just because it's crazy and a little frightening. Okay, so all right, let's talk about some half-life a little bit. So this question gives us the definition of a half-life. Half-life of a substance is the amount of time it takes for half of the original amount of a substance to decay. Alright, so how long it takes for half of it to be gone. You may start off with 10 grams of a radioactive material. So if you want to know the half-life, that's how long it takes for there to only be 5 grams left, right? Half of whatever you start with. So one thing that this is really useful for is in medical settings, because this is more or less how your body is going to filter off any drug that you ingest. So whenever you ingest some sort of drug, it gets into your system, and then your liver or your kidneys, I think it probably depends on what type of drug you have taken, what does the filtering more there, but they're going to filter out of your blood that whatever medicine it is that's in that in your bloodstream, and so it takes a percentage of that away. So each medicine is going to be different depending on how it is made, but we're going to come up with a hypothetical medicine here, and the half-life of it is 4 hours. How much medicine will remain in the bloodstream after 13 hours if the initial dose was 800 milligrams? So we are starting with 800 milligrams of this medicine. And we want to know how much is going to be in the bloodstream after 13 hours. Now, if that was 12 hours, this would be pretty easy to do, right? Because we could just make ourselves a chart. If we've got time and hours and milligrams of medicine, at 0 is when you take it, so you have 800. If you have a 4-hour half-life, after 4 hours, you would only have 400. You'd have half of it left. After 8 hours, you'd have half of that, so you'd have 200. And then after 8 more hours, you'd have 12, so you'd have 100, right? So if we did this one more time, at 16 hours, you're only going to have 50 milligrams. So I could like make an educated guess that I'm somewhere between 150 as far as how much medicine is in my system. But that's not a precise number. And depending on what you are dealing with, you may need a really precise number. So, so I've got 800. Don't put this on there. 800. What is my growth or decay factor that I'm going to use here? We're going to use 0.5 because that is half-life, right? So half of it is going to remain. And I'm going to put a X right here for right now anyway. And that X right there is my number of half-lives. Right? It is not my number of hours because it's not going to be cut in half every hour. It's going to be cut in half every 4 hours. Right? So if I want to know 13 hours, I need to know how many half-lives this would be. So how would I find that? Divide by 4. So I'm just going to do 13 divided by 4, which is going to give me, what, 3.25. So rather than plugging in 13, I'm going to plug in 3.25. So I would have 800 times 0.5 to the 3.25 power. And so 800 times 0.5 to the 3.25 power is going to give me 84.090. Around that to 3 places, milligrams here. Be my answer. Which is reasonable, especially if we think about our table that we made over there, right? This can be really, really important depending on what type of medicine you're looking at. If you just took 800 milligrams of ibuprofen and you don't have something wrong with you, that causes ibuprofen to make you sick, or you're not a small child or something, if this is, then, if you take it again, take a little more, a little less, as long as you don't abuse that over a long period of time. We're not talking life-threatening results here. But several years ago, I had to have like an outpatient procedure done, and the doctor told me as I was about to be put to sleep that they were going to give me whatever medicine it was that I can't remember the name of, and he said, "You're probably familiar with it. That's Michael Jackson's drug of choice." And that was not a funny comment whenever they were about to give that to me, because we all know that Michael Jackson died of drug overdose because he was having basically anesthesia given to him so that he could sleep. So that did not make me feel very comfortable there. But thankfully, whoever, the anesthesiologist that was giving me everything, had everything calculated out fine. It was okay. But anesthesiologists are, they are really, really, really important and have your life in their hands, because they are giving you strong medicines that can easily kill you if they give you the wrong dosage of it. So it always makes me really nervous anytime me or any of my family has to be put to sleep, because it's, very, not that anesthesiologists make a ton of mistakes, but it's just they could, and there's also reactions they may not anticipate. But if you are an anesthesiologist, I imagine that you would do tons of calculations and stuff like this, knowing what to give when, and you got all kinds of more factors here, of course, that you have to consider. So, kind of interesting stuff. Another really common application of this is going to be carbon dating. So if you are digging up anything really old, you would like to know exactly how old it is, and it's not like you're going to find dinosaur bones that conveniently have a date stamped on the bottom of them, right? So, or even if you're finding artifacts such as, pages of things that were written that are not nearly as old as dinosaur bones but are super old, it's probably not going to conveniently tell you the date that it was written in. So, so carbon dating is used a lot for finding anything super old. And carbon-14, which is what they looked at for that, has a half-life of about 5,730 years. So, again, I'm not an archaeologist that is doing all of this stuff. So I do not know exactly how they decide that a bone that was uncovered has 27% of the original carbon. I don't know how they decide how much carbon should have been there. And I will say, you know, carbon dating is not going to give you a very specific time period. Often it'll give you a wide range of values because they have to kind of estimate how much was supposed to be there. So, so we're supposed to estimate the age of the bone. What information are we missing here? Do we know how much substance we began with? We don't know how much carbon there was, right? There's no initial value here. But this is a lot like the problem yesterday with Alfredo's money, right? It didn't matter whether Alfredo had $541 or if he had $10 or if he had $1,000 or a gazillion dollars, right? It took the same amount of time for that to double. So it does not matter that they did not give us the initial amount here. I know 27% of it remains, so I can just make up a starting value. A really easy one to do is just do 100, right? So let's say we started with 100, and then we're talking about half-lives, so we're going to put a half here, to the x power, but remember that x right there is our number of half-lives. It is not our number of years. So, if I know 27% of the carbon is remaining, if I started with 100, what would I put over here on this side? How much is left? 27, right? So 100 is really nice because it makes it really easy to do that. You could use 1 really easily and have 0.27. You can use whatever number you want and it will still work. You'll just have to find 27% of that number over here. So we want to solve this for our x. So Jackson, how do we solve this for the x?
You divide the 27 by 100 first.
Correct. So we've got to get rid of this 100 right here. So 27 divided by 100 is just going to give us 0.27 equals 1/2 to the x power. Good. So we'll do log base 1/2 on this side, which will cancel, and log base 1/2 on this side, which I can do in my calculator. So log of 0.27 divided by log of 0.5 is going to give me 1.88896. I'm going to keep that number in my calculator. And that is going to be my x. But 1.88896 years is not, we would not be carbon dating if it was 2 years old, right? You're not going to go find, get you a metal detector and go to the beach and find somebody's watch or something on the beach and go carbon date it, right? Because it's not old enough for us to carbon date. So this doesn't make sense. But x, what does x stand for? It is our number of half-lives. So each one of these is 5,730 years, right? So this is 1.88896 half-lives. And half-lives for different substances are different, but they tell us this one is 5,730. So we take this number, multiply it by 5,730, and we will get 10,820 3.791 years. Now, I'm sure if you were carbon dating something that you would not give that specific of an answer. You would give some sort of range between maybe 8 and 12,000 years old. But this would be our answer here. And that would make sense. If something's 10,000 years old, you would definitely carbon date it. Okay, questions? All right, we've got one more that we're going to look at. This one is really important, but may not currently apply because car prices are crazy right now. My van was acting up over Christmas, so my husband just decided we were going to sell it and get something new, and we did. And car prices are just like crazy right now. I have known multiple people right now that have sold their vehicles for more than they paid for them whenever they bought them, and they've driven them for 2 or 3 years because there's this shortage on chips. Cars aren't making new cars, and so even used stuff is through the roof. So it was a horrible time to buy a car, but we were also afraid that my van would just quit, so we did it anyway. But so right now is sort of an exception to what's happening right here. So you can kind of ignore it for the strange times of what's going on right now in the world. But normally, what happens is if you buy a car, it begins depreciating as soon as you drive it off the lot, normally. So if you go pay $43,000 for a new car, as soon as you drive it off the lot, it's not worth as much as it was whenever you bought it. And it is going to depreciate as it gets older, right? And unless you have some sort of car that is like a collector or something and you just sit it in the showroom and rub on it is all you do with it, your car is going to decrease in value. Sometimes I hear people call cars investments. Cars are really terrible investments if they're ones that you actually drive, because cars, are going to decrease in value. If you drive them, they are going to wear out. They're going to get older. They are not going to be as worth as much money as they were whenever you had them. Unless, again, you can get the classic car thing where you restore something or, eventually maybe it might go back up. But for most people, you drive them, they start to break down, you sell them or junk them and get something new. So cars are a terrible investment if you're going to invest your money in cars, regular cars. They are a necessity. You need to have one, especially, or in most places that we live around here anyway, you need to have one to get from place to place. But you're not making money on a car normally. Now, some people do buy them, flip them, do things like that. You might can make some money doing that. But we're just talking about regular people buying a car. It's going to depreciate. So the way that this happens is that it's going to sort of lose a percentage each year. And each car is going to be different based on the economy, based on its reliability, demand for it, all of those things. But this is a relatively realistic situation here. If you buy a $43,000 vehicle, it may depreciate about 11% per year. That could be realistic depending on what kind of car it is. So we want to know how long it will take for the car to be worth less than half of its initial cost. So we've got 43,000. What number are we going to use for our growth or decay factor here? Is our value going up or down in this case? Down, right? So we have to take 100%, and it is losing 11% each year, meaning that it retains 89% of its value. So that's going to be 0.89 is what we're going to put right here, and then we'll put X here. That will be our years. So if we want to know when it would be at half of its value, because anytime after that's going to be less than half. We would just put 2,100 or 21,500 right here. Okay. So Blaine, what would we do to solve that? Good. So we got 21,500 divided by 43,000. I should not have had to do that in the calculator. I should have known that was going to be 1/2 because I did 1/2 of that. And then we've got 0.89 to the x power. Blaine, how do I solve that to get rid of that 0.89? Good. And so log of 0.5 divided by log of 0.89 is going to give us 5.948 years. So about 6 years. Which, depending on what kind of vehicle you've got, is probably pretty reasonable. That's actually probably retaining its value fairly well in a regular economy in that case, because being worth $21,000 after 6 years is probably still pretty good. So remember this. Also, know that if you go buy an $80,000 vehicle and you finance it for 12 years, that is not a good idea. It's going to be worn out. You're going to owe more money than it's worth. If you wreck it, you're going to be in big trouble. So, be careful. Those. Alright, questions? Alright, so the assignment is to finish that worksheet. So, a few of you had already done it or parts of it. So, if that is you, then I do not have anything right now. I may take the last like 10 or 15 minutes of class, and we may begin those notes that we're going to do on Tuesday, just so we don't have as much to worry about with that. So, let's see how far we get.